Our whole world runs on code. So how can we really know our digital lives are secure? Turns out the answer isn't just a bigger firewall. Nope, it comes from somewhere way more fundamental, pure logic. Today, we're going to explore how we can use a pretty sophisticated logical framework to literally build trust right into the fabric of our digital world.
Okay, let's really dig into this. When you send a secure message, you trust it gets there safely. But what is that trust actually based on? Is it a feeling, an assumption? In the world of security, that is just not good enough. We need something concrete, something we can verify. So the real question is, can we stop hoping a system is secure and start mathematically proving it?
All right, here's our game plan. We'll kick things off with the core problem of digital trust, then introduce a blueprint to solve it. We're going to look at its two key building blocks, the logic of structure and the logic of belief, see how they snap together to build verifiable trust, and finally, we'll talk about why this whole formal approach really is the future.
So, first up, the digital trust problem. And this is all about making a huge shift in how we think about security. Moving from just hoping for the best to actually proving we have the best. Here's the most crucial point. Assumption is the absolute enemy of security. We just can't cross our fingers and hope our encryption works. The real goal here is to use the power of advanced logic to create formal guarantees, I'm talking mathematical certainties, that our systems will only behave in ways we can trust, period.
So how in the world do we do that? Well, that brings us to our blueprint for security, this really powerful framework called Modal Type Theory. You can think of it like a set of architectural plans for building truly trustworthy systems right from the ground up.
And here it is, Modal Type Theory, or MTT for short. It's not just one idea. It's this brilliant combination of two powerful fields of logic. See, on one hand, you've got the rigid, provable structure of type theory. And on the other, you've got the nuanced, expressive power of modal logic. When you fuse them together, you get a powerful new language, one that can not only describe security, but actually enforce it.
Okay, so let's check out our first building block and see how this all comes together. We're starting with the foundation, the logic of structure, which comes from something called type theory.
So what is type theory? Honestly, the best way to think about it is like a super strict grammar checker, but for math and computer programs. It sets these incredibly precise rules for how you can build proofs and structure code. If something doesn't fit those rules, if it doesn't, type check, the system just says nope and rejects it. This creates that rigid, unbreakable backbone that secure systems are built on.
And this isn't just some academic theory, Type theory is the engine behind real-world proof assistants like Nupril and Coq. These are actual tools that let engineers mathematically prove that a piece of software will never crash or that a complex crypto protocol has zero loopholes. They're used to verify that our most critical systems are built correctly right from the start. Now, having a rigid structure is awesome. But security is about more than just structure, right? It's about what a system knows, what it believes, and what's even possible. And that brings us to our second building block, the logic of belief, which is the whole world of modal logic.
Modal logic lets us go way beyond simple true or false statements. It gives us a formal language to reason about more nuanced ideas. For example, we can ask questions like, is it possible for an attacker to know this key? Or is it necessary for this program to believe this message is authentic? It's basically the what-if engine that lets us model all the complex scenarios of digital trust. And this slide right here shows you exactly how the blueprint comes together. You start with the strict, unbendable structure of type theory. Then you layer on top the expressive what-if power of modal logic. And the result? You get modal type theory, a complete language that lets us finally define and, this is the key part, verify trust itself.
Okay, so we've got our blueprint, but what can we actually build with it? Let's dive into the practical applications and see how modal type theory is used to construct verifiable trust out in the real world.
Using this framework, researchers are building some incredibly precise tools. For instance, they can create a logic of reputation that formally proves whether an online agent is trustworthy based on its past actions. Or they can run a security protocol through a verifier to prove mathematically that an attacker can never steal the key. It's all about making these security concepts measurable.
This quote just gets right to the heart of it. Inside this logical system, the word trust stops being this vague, abstract idea. It becomes a concrete mathematical function. A system can literally check if a new piece of information is consistent with everything it already trusts. If it is, trust is maintained. If not, it's rejected. It's binary, it's provable, it's verifiable.
And get this, the framework is so expressive, it can even model different ways of not trusting. Think about the difference between distrust and mistrust. They sound similar, right? But distrust is simple. Your system sees some inconsistent information and just rejects it. Done. But mistrust, that's more complex. That's when new information comes along and forces your system to revise something it thought was true. Being able to formally model that distinction is just a huge leap forward.
All right, let's bring this all home. Why does a deep dive into formal logic actually matter to any of us? Well, that brings us to our final section. The future is formal.
So here's the big takeaway. As our world gets more and more interconnected, building our future on systems that we just hope are secure, well, that's not an option anymore. Formal frameworks like Modal Type Theory are the tools that finally let us move from hoping to knowing. They're what we need to engineer a future that's secure by design, not by accident.
And that kind of leaves us with a final thought to chew on. Imagine a world where the security of our most critical systems, our banking, our communications, our infrastructure, isn't just a promise, but a mathematical proof. I mean, if we can embed this level of verifiable trust into the very code that runs our lives, what does that enable? What kind of future can we really build on that kind of foundation?